Okay, so actually, somewhat to my surprise, we managed to do most of the things we wanted to do with prompt geodesics yesterday, and therefore we are in a position today to state and prove Penrose's singularity theorem. And if you compare it with Hawking's singularity theorem, which we already did last week, basically with Hawking, what we had were two steps. One was to show the existence of focusing if the initial condition is suitable, focusing in the past, and then because theta is positive at the present time, the expansion, and then to say that with global hyperbolicity there's a contradiction, and there cannot be any curve that goes far into the past, and therefore space-time is geodesically incomplete. Now what we want to do is to show that the interior of a black hole is geodesically incomplete. Ideas are similar. Raychaudhuri equation, which shows the existence of focusing, is also similar, and I'll write it now. The main difference though is that from a space-like hypersurface there is one time-like direction in the case of cosmology. In the case of black holes, on the other hand, we actually have a space-like co-dimension 2 surface with two null directions coming out, and we really need for both of them to focus in the same direction before we can conclude that space-time is geodesically incomplete. And that property of both focusing in the same direction is exactly the existence of a trapped surface. So we need to add that in the mix, and then there's a theorem and it will be done, it will be over. So I'll just recall from a very early lecture in the course when we started doing geodesics that we have a Raychaudhuri equation, the null one. I mentioned once that this equation was actually never derived by him. It was actually derived by Sachs. But it's generally credited to him because he did the time-like case and the idea came from there. And so you have an expansion, but it has a hat, and that's because this is a quantity which is projected onto a onto a co-dimension 2 hypersurface. So everything has a hat in this discussion. Lambda is the affine parameter. Obviously we can't use proper time because that's 0 in the null case. Then this is a different coefficient, d minus 2 instead of 1 over d minus 1. Then there's minus trace sigma hat squared, the shear term. Then there's no rotation term because we choose hypersurface orthogonal geodesics. And finally we have this, where u is the tangent vector. This is also r hat, yeah, and u is the tangent vector to the congruence. Now we need to say which congruence we are dealing with. So just to be definite, I'll choose lambda to be u, and then this is the expansion theta u. And then of course one can do the same thing with V. And from the Einstein equations, R mu nu will be equal to 8 pi g T mu nu plus 2 upon d minus 2 g mu nu lambda. To get that last term, we have to project this and also contract it with two null vectors. And what happens is that, so therefore R mu nu u mu u nu is actually equal to 8 pi g T mu nu u mu u nu. But this term isn't there. So because g mu nu mu is 0 because these are null. So that term just isn't there. Then when we project, so unfortunately I have a notational conflict. There's a concept of hat on t, which we defined once as t hat is equal to t minus some number times 1 by t minus 2. And here also, if I contract with u nu, then this term doesn't contribute. So therefore I can as well just use t. So otherwise this should have been t hat if this was r. And then when we put everything in and the cosmological term drops out, then we basically get the Raychaudhuri equation to have d theta of u du is whatever terms I've written, and the last term becomes minus t mu nu u nu, and the null energy condition says that this is greater than or equal to 0, in which case, or greater than 0, actually never sure what people use, but I actually in some theorems will use greater than, in some will use greater than or equal to. I mean in some theorems in Wald's book, for example, they use one or the other. I'll simplify things by only telling you one theorem, and I'll tell you what condition we exactly need. And well, there's nothing more to do to analyze this equation beyond what we already did. So we start by bringing the first term on the right to the left side, and we find that d theta u by du. I should really put a partial derivative because it's with respect to u at v fixed, plus plus 1 by d minus 2 theta u squared is less than or equal to 0, and then integrating gives that theta of u inverse at a time u is greater than or equal to theta of u inverse at the time u equals 0 plus 1 by d minus 2 u. And now if we are going in the forward u direction, so we think of u as a null time, and if we go in the forward u direction, and if theta is negative to start with, then this whole thing is eventually going to become 0 when u reaches some value. And that value, so this thing goes to 0 when u is equal to d minus 2 upon theta u of 0. And that's when therefore the expansion diverges. And that's, as we've seen, is a sign of focusing. So this gives focusing exactly as before, and the amount of time it takes for geodesics to focus in the null coordinate u is that thing. And now all the same equations are true if v is the null coordinate. One point which is a little subtle and I want to emphasize here, sometimes we use synchronous coordinates, but in synchronous coordinates either u or v is a null coordinate. We can't have both. Okay. So what we do is we go to the synchronous coordinates where u is a null coordinate, and then we study the congruence and the focusing in the u direction. Then we change our coordinate system to the other synchronous coordinates in which v is a null coordinate, and then we repeat everything. Of course, we don't even need to repeat because it's just the same as before. But it's important that you can't actually treat both as null coordinates in the same coordinate system. Okay, good. So now by now we've done the Schwarzschild solution, and we know this feature about it, which is that the sphere, the angular sphere, as once r becomes less than 2 gm, has both the outgoing null directions pointing inwards, and we've seen that from the, I guess most simply from the, let's see, which diagram do we want to use for that? Finkelstein, I guess it's called. So the idea, now I don't remember what a Finkelstein diagram is. R. This is R. And yeah, and here is the horizon. And what happens is that far away the light cone looks like that, but here the light cone starts to tip, so that once you are exactly here, the light cone looks like that, and then it looks like that. And one of these is the u and one is the v direction. And so we see that because of its tipping over, both are pointing inwards. And that's the condition for this Penrose's theorem. So to generalize that, we define a trapped surface in a general situation. Trapped surface is a compact d minus 2-dimensional space-like submanifold such that both its future directed null expansions, by which I mean theta of u and theta of v, are negative. Because a negative null expansion causes focusing in the future, and this causes sort of double focus. Okay. Now just to quickly remind you, supposing I had, this doesn't happen in normal spacetimes. And just let's remind ourselves why. So it doesn't happen, for example, in Minkowski. So just to simplify things, I'll write 2 plus 1d Minkowski. So its metric is minus 2 du dv, and then plus u minus v squared by 4 d theta squared. We've done this coordinate system long ago. Now we have to calculate the quantity. So what's the quantity of interest? It's called capital A. So actually I forgot to write remind you what's the definition of the expansion. So I think A is not a very good notation, but for now it will have to do. So it's root det of GAB. I think I've been using consistently AB to run over the d minus 2 space-like directions. Okay, and then theta is just del u of A upon A. This is the same kind of definition for the time-like case, but in the null case, the del by del t is replaced by del u, and instead of this determinant of a 3 metric, which is the spatial metric. This is the determinant of a 2 metric. So what is GAB over here? Well, GAB is just this metric, and the determinant of GAB, if I take this metric here, I get half u minus v. And now I can see that del u of A is, it's I guess half on, half. So it's greater than 0, and del V of A is minus half, so it's less than 0. So this is the normal situation, because this is the quantity which you use to define A. Its derivative with respect to u and v will be opposite. Okay, now you may object that I should have put a mod around u minus v, but I think I'll still get that del u A upon A is positive or negative. This is probably not the right way to write it. So it's this. But now supposing u is greater than v, then this is equal to u minus v. And then del u, so if u is greater than v, then del u A is greater than 0, del v is less than 0. And if v is greater than u, it's just reversed. The important point is that there's only one positive and one negative. But in Schwarzschild, as we saw, both can be positive, and the trapped surface is one where indeed that is true in the modular case. And this is enough, coupled with what we've done yesterday, to state Penrose's singularity theorem, and then we'll go through the proof. So again, as with the Hawking case, there are many theorems, and I've picked one, and this is actually a little too restrictive, but let me write it first. So, globally hyperbolic spacetime with a non-compact Cauchy hypersurface. And satisfying the null energy condition So then if M contains a trapped surface, I'll use T for trapped surface. It is M is geodesically incomplete. Both these assumptions will be used in a crucial way, globally hyperbolic as well as non-compact Cauchy hypersurface. So let me first comment on them. Globally hyperbolic, we sort of all agreed is a nice thing to have because we have a good initial value problem. But unfortunately, not all black holes are globally hyperbolic inside, and in particular, Kerr black hole, actually the extended one, not just the exterior. So I haven't I haven't described the curved black hole in this course, but you might know already that it has an inner and outer horizon. And as long as you're outside the inner horizon, you're good. It's globally hyperbolic. But the extended curve is not globally hyperbolic. And so that causes a little problem with this assumption, because we are trying to apply it to generic black holes, and actually generic black holes are mostly curved black holes, of course. Yeah. So that's one problem. The second one is Minkowski has a non-compact Cauchy surface. Of course, we are not really trying to apply this theorem to Minkowski, but fortunately, we can replace this by asymptotically Minkowski, and now it applies to all asymptotically flat black holes, and that's good. So this restriction is not too bad, but it has to be revisited if I want to look at ADS or DS type of black holes. And if you ever want a larger list of theorems that are applicable to the asymptotically flat case, you'll find them typically in Hawking-Ellis's book and also in Wald's book. What you won't find in Wald's book is any discussion about the ADS type of black holes. They're simply not there. So that one has to. So I haven't prepared anything to tell you about those. So I simply won't discuss them now, but maybe we'll come back to it another time. Okay. Okay, so now let me give you some intuition about how the theorem is proved, and then we'll go through the proof.
So what is NEC?
NEC, null energy condition. So for this, we are going to look at the key player in the proof is J plus of T. T is the trapped surface and J plus is its causal future. So as you know, J plus of literally anything is even a point is the same dimension as the manifold, and it has a boundary. So the key players are J plus and boundary of J plus. Actually, the key player is boundary of J plus, I should say. Okay. So this is of course a null hypersurface. That's always true. Now, we are going to show two properties of this, that it is achronal, and two, that it's compact. Compactness in particular will require using global hyperbolicity as well as using the trapped surface. This is more generally true, and we may have already said this earlier. So we are going to do these, prove these two things. That's the bulk of the argument. I'll remind you that for a curve, achronal and prompt are the same thing, but J plus, the boundary of J plus is not a curve. It's a hypersurface, null hypersurface. And you can only ask if it's achronal, and it turns out to be And now there's a theorem that I think we already stated that, so this is, okay, so this is one step we have to prove, this is the second step, and third step is a theorem that any achronal hypersurface is topologically equivalent in other words homeomorphic to part of sigma, which is the Cauchy hypersurface. So we are given that it's globally hyperbolic. So there is a Cauchy hypersurface sigma, and any achronal hypersurface must have a topological map, that means a map preserving continuity onto some part of the Cauchy hypersurface. And then we'll find a contradiction because sigma is non-compact, and we'll show that boundary of J plus is compact, and that will lead us to a contradiction. Of course, it's a compact subset of sigma, but we'll still find that there's a contradiction. We'll show that actually it has to be both closed and open in sigma, and if sigma is connected, then nothing can be both closed and open except the whole of sigma. And boundary of J plus cannot be the whole of sigma for the reason I just said. One is non-compact and the other is compact. So that's the sketch of the idea. And so most of the work consists of proving 1 and 2. And actually this theorem I think I've already proved, or I don't remember if I did it in class, but it's certainly in my notes. Does anyone remember if I did this thing? So this is part of the discussion. We had first a discussion that any Cauchy hypersurface is topologically equivalent to any other. Okay, that was done using the global time function. Then for achronal, we had to do something, well, Cauchy hypersurface is also achronal. But then we said, okay, more general achronal hypersurfaces, even if they are not Cauchy, they will at least have to map to some part of sigma, and in a homeomorphic way, and that's basically then leads to the contradiction. Okay. Good. So the steps to prove compactness of J boundary of J plus is going to take some time, and there are 3 steps to prove that compactness, one of which is proving the achronality. So I'm going to write it again. So this we want to prove for boundary of J plus. The second step, this is the second step actually now. The first step is to prove that J plus and boundary of J plus are closed. And in fact here what I'll do is I'll consider J plus and its boundary for any subset K of the manifold. It doesn't have to be a trapped surface. These are relatively simple theorems, and later we'll just put K to be the trapped surface. The second thing we'll prove is that it's achronal, that boundary is achronal. And the third thing we'll prove is that boundary of J plus of K is a manifold, though not necessarily smooth. And again, if you remember what I did many lectures back, we discussed something very similar for the boundary of I plus, the chronological feature. Okay. Now let's remind ourselves what is the basis for each of these things. So proof of one. So actually what will happen is in this lecture a whole lot of things that we spent a lot of time proving quite some time back are going to come back and be used, recycled to prove this important theorem. Okay, so we showed that boundary of J plus for a point is closed. The way we did this is as follows. We started with a point P. Then we assumed that, so recall how we proved this. We are going to, because the proof for the case of J plus of K is very similar. So recall, as usual, we assume the contrary. So therefore we assume that boundary of J plus is not closed. Not being closed implies there is a sequence of points in boundary of J plus of P with a limit point P prime, which is not in the boundary of J plus. So any set is closed if every sequence of points has a limit point which is in the set. So if it's not closed, then there must be at least one sequence such that the limit point is not in the set. So P prime is not in boundary of J plus of P. Okay. Oh, sorry, I'm trying to prove that J plus is closed. So right now I'm not even going to use boundary. We'll just use it for J plus.
We proved this is a global hyperbolic.
Yes, it follows from global
We
hyperbolicity.
proved that J plus K, J plus is compact.
Sorry?
We proved J plus is compact in causality.
We proved that J plus is compact or boundary of J plus?
No, we proved J plus. J plus is compact. Compact then is closed.
Closed, I remember.
Compact we proved.
No, compactness. Okay, we are trying to prove compactness of the boundary. That requires a lot of work.
We didn't prove that.
I don't think we proved that. So anyway, at the risk of repeating some things I might have said earlier, let's quickly show why J plus is closed. So there's a limit point. It's just a repeat of what is I did, as I said long ago. So there's a point P prime, which is a limit point, but it's not in J plus of P. So take this point. So now let's draw it here. This is P. And here there's a point P prime, which is, so this point is in boundary of J plus, this point is in, this is the point, it's better if I draw it. This is the point P, this is boundary of J plus of P, and there's a it's not closed, so there's a sequence of points such that somehow I'm drawing it exaggeratedly far away. There's a P prime which is not in boundary of J plus. Okay, it can't be there obviously, so it has to be here. Okay, so now let's look at the future of this, the J plus of this point, and let's pick an arbitrary point Q over here. And then we study the causal diamond of this Q with the original point P. That rectangle is the causal diamond, dpq. Okay. Now, I won't repeat all the details, but one can now show that this point P prime is in the closure of dpq, but it's not in dpq itself. It's not possible to draw. The reason it can't be in dpq is that it's not in. What is the reason it's not in dpq? dpq is the intersection of j plus of p and j minus of q. Oh, sorry. As usual, I shouldn't have. There's a sequence of points. Yeah, I guess. I'm not even sure where this point p prime could be, but it's the limit of a sequence of points such that all the points are in j plus of p, but p prime itself is not. I don't know where to draw it.
Are the sequence of point in the causal diamond?
Yeah, because that's they are because they are in j plus of p, and yeah.
We know that causal diamond is compact. And in the sequence of point in causal diamond, there are.
Oh yeah, that's exactly.
The limiting point should also be in causal diamond because of the various.
Yes, but we don't start by assuming that. We start by saying that let j plus itself. Okay, actually, so if we know causal diamond is compact, I think we can show that j plus is compact just by taking q to infinity, right? I think we discussed this once. I think that's simpler. So then I don't know why I'm wasting my time. Let's assume we have proved that j plus of a point is compact. We have indeed, as you say, proved it. Yeah.
Boundary and the compactness of boundary.
Yeah. Anyway, this was how we basically proved it, and the important thing is the causal diamond itself being compact came from a space of curves being compact. We used the curves from P to Q inside the causal diamond and took a limit, and from that we got the fact that causal diamond is compact. And actually, why do the whole thing again? I think I'll just write over here. We already showed that j plus of p is closed from compactness of dpq. That's quite sufficient. Okay. Okay. Now, however, there's something slightly different here because we are considering j plus of k. And for this, this will follow, will similarly follow compactness of this. Follow similarly. Okay, I should have said compactness of dpq, which follows from compactness of CPQ, which follows from global hyperbolicity. Okay, but now that we are looking at j plus of a subset k, so this will follow from compactness of not CPQ but CKQ, which is the space of curves starting on a subset K anywhere and ending on Q, but causal. Okay, so proving that this is compact is very similar to proving that this is compact, where the initial and final points are fixed, and I left it as an exercise. So supposing we assume this now, then we can prove the compactness of j plus of k as follows. Actually, it's the same proof, but maybe I should just repeat it for people. Yeah.
Can't we just say that P is in K?
No, I don't think we can just say that. If P is in K, then of course you have curves from P to Q, that's compact. But the space of curves, the space of KQ is a much bigger space. It's all curves from K to Q.
Yeah.
Okay? And so even if the space is compact for each, you're saying if it's compact for each P in K, then it's the union of it should be compact? That no, but it's an infinite union. Yeah, that's probably okay.
Yeah, that's what I was thinking.
Yeah.
Like P is arbitrary in K.
Yeah, that's fine, but we have to take an infinite union over all P. Anyway, let's just go through it quickly. So, again, assume contrary. Assume the contrary. J plus of K not compact. Then there is a sequence of points Qi, which are all in J plus of K, but the limit Q is not in J plus of K. This is what happens if J plus of K is not compact. Then we consider a family of curves which start on this K. Here are the Qi's and here is Q. So these are the Qi's. So we consider curves like this to each of the Qi. Okay? And now this set of curves exactly forms the space CKQ, QI, CKQI. So compactness of CKQ is the statement that if I have many curves in this space, then they all converge to a limit curve or a convergence curve as we defined, as we explained once. And that curve must end at Q. Okay. So CKQ compact implies sequence of curves from the set K to Qi converges to a curve K to Q, and everywhere causal is used. So sequence of causal curves converges to a causal curve. All these theorems are only about causal curves. And if there's a causal curve K to Q, this implies that Q is in J plus of K by definition of J plus of K. So actually our assumption was wrong and therefore J plus of K is closed. Okay. Huh?
It's compact and closed.
No, it's not yet, huh?
It's compact or closed? Only closed.
I think we've only proved closed, no? Closed is just the statement that it's, no, compact we haven't done yet. This is just closed. Closed is the statement that if you have a limit, then the limit point must also be in the set. And closure is the process of adding those limit points. So the closure of any set is closed, but the set might not be. Okay. Good. Okay. Now we have to do the same for the boundary of J plus K. We want to show that that's also closed. And here, if indeed the boundary was not closed, it's even easier to see. This is where I drew a diagram 5 minutes ago. if the boundary is not closed, then you have a sequence of points like this on the boundary, those qi's, these are the qi's now. But the limit q being not in boundary of J plus is somewhere here. Okay. Now the problem is if q is not in boundary and it's somewhere here, then of course there exists an open set which is fully contained in J plus and not in the boundary. And since these points are supposed to converge to q, then for sufficiently large values of I, they must be entering there. But then I've said they are on the boundary, that's a contradiction. That means they have to get out of the boundary for some large value of I just in order to converge to q. So the situation as I've drawn it, which looks absurd, is actually absurd, and therefore we conclude that del J plus of k is also closed. So here we proved that J plus is closed, and here we proved del J plus is closed. So far so good. Okay. Now achronality is the next one. I have a feeling this also we have proved some time ago. But in fact it's good to do it now again because it's very similar to how we study prompt null geodesics. So again we assume that it's not achronal. In that case there must be at least one pair of points P and Q that are also connected by a time-like curve. Okay. Now this time-like curve, being time-like, is not prompt. So there has to be, whenever something is not prompt, there has to be something more prompt which reaches earlier, and so there has to be a curve like that which gets to the same location as Q but earlier. And this can't happen because as long as Q is on the boundary of J plus of K, there is no point earlier at any fixed time. So this actually says that even though we assumed P and Q to be on the boundary, Q has to be actually inside the bulk in order for there to be a possible earlier time. And so it's achronal. It's very simple, this part of the proof. Okay. And so actually there is a corollary to this result of achronality. One corollary says that any P in, this is for a generic manifold, any P in this space can be reached by a prompt null geodesic from K, and similarly any 2 points P and Q both in this space can be connected by a null geodesic prompt null geodesic lying completely in this space. So these are things we'll use in a few minutes. So achronality was simple. And now the third one, so if you remember quite some time back there was a theorem which said the boundary del I plus of any set S is a codimension 1 achronal set, and it's a topological submanifold of M, and we gave a proof which I remember from that time. It's quite similar to that, but I'm not going to go through the proof again. One thing to note, and maybe I had already noted it at that time, is that we are claiming this boundary is not necessarily smooth as a manifold. So we are saying it's a manifold but not necessarily smoothly embedded. And a trivial example, if you like, is just take your set to be a point. Then the boundary of J plus of K is the light cone, this and this whole surface of rotation, and it's not smooth at this point. At least it's not embedded into space-time in a smooth way. Okay. So all the properties that we need have been proved, and now we are finally on to the stage of proving that boundary of J plus is compact. And we want to apply this to any. So now actually it's true for a. Now we'll apply it for a. We don't need as yet. I don't know if we need for it to be trapped, but we need for it to be a codimension 2 hypersurface. Till now we were just taking K to be any set. Could have been a point, could have been a, sorry, take that, not codimension 2 hypersurface, that doesn't make sense. Codimension 2 surface. But up to now K could have been any set, but now we'll take it to be a specifically a codimension 2 surface, so that there are two null directions coming out from it. And we'll start with a prompt, prove this is compact. And here is T. And now we consider a null geodesic that starts at a point P on this surface and travels in the U direction up to a point Q, and then I continue it further up to a point Q prime. And let's assume this is a focal point. So I need not draw, there must be another geodesic which also does that. So this is a focal point. This P to Q I am taking to be prompt, but given that this is a focal point, the rest of it Q to Q prime cannot be prompt. Okay. So let's denote the whole curve. So first let's denote the PQ curve by gamma PQ. So that's this segment from here to here. And the whole thing from P to Q prime by just gamma. Okay. Now, since gamma PQ is prompt, this implies that Q is in boundary of J plus of P. And since boundary of J plus of T, which is the thing I'm interested in, is the union over all P's, Q also lies in boundary of J plus of T. Okay. And the set, so usually we think of gamma as a curve, but you can think of gamma PQ as a set of points, then it's compact. Because it's just a line in space-time and it contains its endpoints. For a line to be compact, it only needs to contain its endpoints. Because it's defined to contain both P and Q. Okay. Now we consider the intersection. By the way, this proof is styled on Witten's lecture notes. Consider the intersection gamma with PQ, the compact set, with del J plus of T. Sorry, we consider the intersection of the whole curve, gamma. Okay, and we show that this is compact. We are about to show that. And that's pretty much the end of, once we show that, we are pretty much done. Why? Because if gamma intersection of boundary with boundary J plus of T is compact, for every U directed null geodesic, we'll also similarly find that gamma V, that is the V directed null geodesics intersection J plus, are also compact. But the combination of U and V directed null geodesics, they span all of boundary of J plus, and therefore boundary of J plus itself will be compact. So it's actually enough just to show this, then the whole thing follows. Okay. To show this, first we show that even though I am intersecting gamma with del J plus of T, this actually is contained in gamma PQ. So the intersection of this with this obviously is contained in gamma and contained in del J plus, but it's actually contained in a subset of gamma, which is the part where it's prompt. Because after Q, since Q is the focal point, this geodesic is no longer prompt between Q and Q prime, so it leaves boundary of J plus. Okay, and so this intersection is contained fully inside only the prompt part of gamma. Okay, so this is one thing. Secondly, we showed that boundary of J plus is closed, and from that it follows, and that's why we did it, since del J plus of T is closed. Therefore, this intersection is also closed. Okay, so this intersection is contained in gamma PQ, which itself is compact, and gamma PQ is compact and it's closed. But a closed subset of a compact space is also compact. This is a simple theorem in topology. And therefore, we conclude that gamma intersection boundary J plus of T is compact, exactly what we wanted. So we showed it's closed, we showed that it sits inside a compact set, and these two things are enough to tell us that it's compact. And now we repeat for every point Q. Actually, yeah, sorry, I said something wrong. I said we sum over all starting points. No, we sum over all ending points. We sum over the focal points, all possible q's in del j plus of t, and by doing this we cover how to say, we argue that, well, just repeat the argument that every such intersection, gamma intersection with del j plus of t is compact. Okay, so this implies that this is compact true for all gamma from k to q. Remember, we don't get to choose the starting point actually, because I'm saying it's prompt up to q and I pick q, then it will start wherever it feels like on k. It can't start at my designated place, it may not, then it will fail to be prompt in general. It has to start in a place where it intersects k orthogonally, and from where it can actually be prompt up to q.
You did T.
Sorry, I meant t. Yeah, and actually good. I'm glad you said that, because until earlier I was working with a generic set k. Now I'm using the fact, first of all, that t is codimension 2, and second also that it's a trapped surface, because that's why I can say this much, by the way, I can do even for an untrapped surface, because the u geodesics will focus in the future, but I can't repeat it for the v geodesics because they may not focus in the future. So I'm still not done. So this is true for all u directed gamma. Okay. Now since t is trapped, above is also true, because remember, a focal point was crucial. Q was a focal point. Having a focal point in the future was needed for this to happen. Basically, the focal point was causing the prompt geodesic to kind of lose steam and stop being prompt after the focal point that we discussed in detail yesterday. So since t is trapped, above is also true for v directed geodesics. And that's the key. Once it's true for both u and v directed geodesics, it basically says that del j plus of t is compact. And that's the key result we wanted to prove. So now it was theorem that we proved long ago. If a Cauchy surface is non-compact but connected, then any achronal hypersurface, which is a submanifold of M, cannot be compact. That was the theorem. So, so compact and achronal both are done. Therefore, contradiction. Okay, I should have said more clearly that all this stuff required that after the focal point we can extend the geodesics, because after we extend them they go out of del j plus, and all this stuff depended on that. But the contradiction says that we can't extend at least some of the geodesics beyond their focal point. So that's the geodesic incompleteness. And that's the theorem.
Why we can't extend some geodesics? Why we can't extend some geodesics?
That's the only assumption that we couldn't prove, right? And since we got a contradiction we've showed that del j plus is compact, but since the Cauchy surface is non-compact, it's not possible for del j plus to be compact and achronal. Because the theorem says that when it's compact and achronal, it has to map to some part of the Cauchy surface, and then there's a step which I might have skipped, which says that Now, that was already proved.
Yeah,
In that we proved that actually so basically just think of it this way. Here's the Cauchy surface, sigma. Here's your achronal del J plus.
Okay.
What you do is the achronality allows you to set up a map between sigma and that. But of course it may not cover all of sigma because this is not a Cauchy hypersurface, though this is. So from this, the time-like directions going out, of course, will go pass through it everywhere. This will have some time-like curves crossing it. Okay? And they can only cross it once, because if they cross it twice, then achronality is violated. So those time-like curves which cross it, produce them this way, they have to cross the Cauchy hypersurface also. So there is a one-to-one map set up between that and this. But we've just shown that this is compact and this we've taken to be non-compact. So there's a non-compact, there's a compact subset of the non-compact space. But then we have to also show, and that's the manifold part, that this set is both closed and open. Okay, it's an open set because this being a manifold allows you to have charts which map it to open sets of Euclidean space. And so once you use that, you'll find that this image of del J plus in the Cauchy surface is open. But its compactness will also tell you that it's closed, and with the closed and open, it has to be either all of sigma or nothing. But it can't be all of sigma because sigma is non-compact. Okay. So some concluding remarks for this part of the discussion. First of all, we know much more about what actually happens in the Schwarzschild case than whatever this theorem tells us. It simply tells us that if you have focal points, then some geodesics are incomplete beyond that. But it doesn't say what happens to them. But in the Schwarzschild case, we know that the null geodesics, future directed, all terminate at the singularity. Okay, here we have not been able to predict there is a singularity. This is the criticism that these are called singularity theorems, but there is no singularity in the theorem. There is only geodesic incompleteness. Okay, that's one. And also, we knew all these things about Schwarzschild before Penrose did his work. Okay, that's just from analysis of Schwarzschild solution, which is much older. So Penrose's work gives a limited answer, but for a broader class of spacetimes. In fact, it doesn't assume the spacetime is a black hole. Actually, we didn't even assume the existence of a horizon for this. We assumed the existence of a trapped surface. However, the trapped surface is found inside, so that's a separate theorem which says that trapped surfaces are found inside and not outside the horizon of a black hole. And from next week, we'll actually be discussing generic black holes in a little more detail, because this is not the end of the discussion. We have many things still to show. This only is the geodesic incompleteness result, or the singularity theorem. I'll summarize in 2 minutes what else we want to show in this subject. One comment I made right in the beginning is that this theorem started with global hyperbolicity, and that's not true in the Kerr solution. So it doesn't guarantee for me automatically that solutions like that, spacetimes like that, are geodesically incomplete. So what can I say? So Wald has a nice theorem with different assumptions. I think it's again a Penrose theorem which he describes along with its proofs. So here you abandon global hyperbolicity, just don't assume it, but instead you assume what are called time-like and null generic condition. I forgot to use this word, but I've already introduced the condition once. So the time-like one is that R nu lambda rho u nu u rho is greater than 0 at least, this is a condition on a congruence, so at least at one point on every geodesic. This is called the time-like generic condition. You would think the null generic condition is exactly this, with u being a null vector, but actually it's not. It's written in terms of the Y tensor, so it's a little more complicated, but there is some such condition. So then what else do we assume apart from that? Obviously we are going to assume a trapped surface. So, well, first obviously we have to assume a energy condition, and for this theorem null energy condition is not sufficient. We have to assume the strong energy condition. Okay, and then we assume absence of closed time-like curves, so stably causal or whatever, and then finally trapped surface. That's obviously there, otherwise nothing is going to happen. So with these four conditions and no mention of global hyperbolicity, you still get a theorem, and the theorem now says that there is at least one incomplete geodesic in the future, but it may not be null. Time-like or null. Now, a single incomplete geodesic is enough to say that space-time is geodesically incomplete. But it's a lot weaker than saying that, you know, in the Schwarzschild black hole, if you go inside, whoever you are, whatever geodesic you're on, will send you to the singularity. If there's only one incomplete geodesic, then you might be lucky not to be on it, and then maybe something else happens for you. So it's much weaker. But it does say that the space-time is geodesically incomplete, because to be complete, every geodesic has to be complete. Okay. Last comment for now, which is actually subject of some misstatements about Penrose's work, and which I'm also guilty of. Penrose did not actually tell us when a black hole forms, because he only said when a trapped surface exists, then the black hole, basically his way of saying it is when a trapped surface is formed, then there's a singularity. Now we have kind of over the decades watered it down to say when a trapped surface is formed, there's geodesic incompleteness. But when is a trapped surface ever formed? It is never going to be formed, then there's no point in this discussion. So there's a very key theorem, and I actually want to talk about it. I have not studied it carefully, so I can't tell you today, and we're also roughly out of time. But Schoen and Yau have a theorem which shows that if sufficiently large, and this is really important actually, sufficiently large mass density in sufficiently small region, so the bounds are given. Trapped surface will form, must form. And this is sort of a satisfactory conclusion, because it is really what tells us that black holes should form. Penrose's theorem really tells us what black holes do inside them after they have formed. Good. Yes. Oh, okay. Okay. Now we have actually 6 lectures left, or less, depending how we all feel. I want to talk about generalities. Let me just say in a few words what kind of generalities. So first of all, cosmic censorship needs some discussion, because again, it's cosmic censorship is the statement that when there's a singularity, it's masked by a horizon. So the thing is, singularity, as you know, or even geodesic incompleteness, spoils physics. It spoils the predictability of physics. But we shouldn't mind if it only spoils predictability of physics for somebody who is never going to come out from a horizon and tell us what happened, because then physics outside the horizon is safe, and as long as we are outside all horizons, we are okay. But it's true in Schwarzschild. There are exotic spacetimes which don't satisfy this, which have what are called naked singularities, not inside a horizon. There are arguments whether those should be allowed, should not be allowed. So that's something we'll discuss and try to summarize the status. Then there's the Hawking area increase theorem. And let me try to see in which order they go. Before Hawking area increase theorem, there's also the theorem that black holes cannot split, but they can join. And that also will use all the machinery that I've already prepared for you in the causality chapter. Basically, the process where a black hole splits, there will be so the way to think about it is, so let's imagine the exterior, or actually let's imagine these disks are like the Cauchy hypersurface for the black hole. Okay, so as you know, time-like geodesics will all puncture the Cauchy hypersurface exactly once. And the point is that if they are future directed, and if the black hole splits, and if the horizon is still a horizon, then the ones inside better stay inside, because otherwise, after this black hole splits, some geodesics which should have been inside the black hole suddenly come out. That doesn't seem, that's not consistent with the horizon being there. So this is the problem, and this is why, well, this is a very crude sketch, but this is the idea of why black holes cannot split. Okay, you have, imagine there's a big Cauchy surface, inside it is this is the part of it which is inside the horizon, rest is outside. Those geodesics which pass through the interior, the Cauchy surface in the interior, must remain inside a Cauchy surface in the interior of the future black holes if it splits. But then somehow it's a discontinuous thing, right? Because how does this geodesic decide if it's suddenly going to go there or going to go there? This is a discontinuous process, because it's not allowed to go out in between. But we'll discuss this. I'm just giving you a preview. On the other hand, you may say, well, the time reverse of this is very confusing, because imagine instead I have two black holes joining. We agree that they can join. Okay, what happens to the fact that there are geodesics going through this and this? Well, all of them need to go through the interior of the black hole and the Cauchy surface inside that interior. But there is no loss of continuity, because there can also be geodesics which are never inside these two black holes, which also nicely go and land inside that one. It's a one-way process. You can go inside a horizon, you just can't leave a horizon. So this process is perfectly okay, and even if you had a bundle of geodesics here, some of which came from outside these two black holes and some of which came from inside, they could all very well smoothly go inside that. Okay, and then of course geodesics which are far away would miss this. That's also fine. They would go through a Cauchy surface, just not in the interior. But here in the reverse direction there is a problem, because there's a discontinuity in these geodesics deciding to go into that black hole or that black hole, and therefore black hole cannot split. That's one result. join but not split. And then there is Hawking's area increase theorem, which says that under any physical process, the area of a black hole must increase. And this will again use Cauchy surfaces, it will use all the kind of things that we've prepared already. And in the process of discussing both this and area theorem, we'll have to define clearly what we mean by the exterior of a black hole, the interior of a black hole, and so on in a general case. And after this, we need to talk about black hole thermodynamics, because the increasing area was the first evidence that there is some kind of entropy law going on. Then as you again know, probably you must have heard that the Hawking temperature remained a mystery for some years, because there wasn't anything available that looked like a temperature, nor there was a process which could generate a temperature. Well, it turned out the missing temperature was the surface gravity, and our proof that it's constant on a null hypersurface on a horizon, actually on a killing horizon, is exactly what we need to prove the existence of temperature. And of course, the Hawking process itself is quantum. So we are now sort of going to be on, this course is all classical gravity, but as you know, classical thermodynamics is really something that comes from quantum physics, but we didn't know it till we understood the microscopic nature of things. So that's the situation here also. The real question is, why is there, if you ask why is there a temperature, then you have to know microscopic physics. And here if you ask why is there an entropy, and here you have to ask the same question. But up until then, at least we can formulate all the rules of thermodynamics just in the language of, or rather formulate all the modifications of thermodynamics which are due to gravity, due to black holes. So we'll do that, and I think it will be done in 4 lectures actually, most likely. So let's see. Okay, any questions?